Hi everyone. Today I'm going to try to motivate stood forward or forwarding or universal references in this little toy example involving a cat and two people. And yeah, my hope is to try to explain why we need the notion of stood forward, why it makes our life easier as programmers. And yeah, so in this example, I'm going to have three structs, right? Cat, Alice, and Bob. And I'm going to remember out for now, but we're going to have these three characters and we're going to have a main method, a main function that interacts with these three entities. So let's start first by defining our cat. So in this case, I want to have the notion. I want to log when a cat is born and when it dies, right? When it's constructed and destructed as such. And the reason is because we kind of get to see the ownership, who this cat belongs to by logging when it's constructed and destructed, which would be otherwise hard to see. And we see that this cat, of course, will have in the real world, it will have like a lot of attributes like age, name, and so on. But in this case, the only data I want the cat to have is a has so boolean variable. And the reason I want to do so is because without this has so boolean variable, the move constructor gets a bit funny because um, if the cat really owns no data, right? Then when I call the move when have a move constructor, when I call a move constructor on it, it kind of duplicates the cat instead of like moving the cat from one owner to the other. So there's not really a semantics I want. And essentially, if I didn't have the have so boolean variable, I would end up having two cat dies, right? Even though in this example there's only one cat. So in this case, the has so essentially represents the soul of the cat, and the semantics this achieves is that I'm only going to create one cat in this example, and as such, there's only going to be one cat born and one cat dies, right? We won't see any instances of like duplicate the cat is being duplicated and so on. So I'm only going to have one cat in this example, and I'm going to delete the copy constructor so we cannot clone the cat easily, right? Technology isn't there yet, and yeah, and I'm also going to define a because I have this has so variable that keeps track of which cat has a soul and which cat is like kind of like empty shell. I'm gonna have a custom move constructor over here that sets the if I construct a new cat C from an old cat, if I construct a new cat here from an old cat C, then I'm gonna set the has soul of this new cat to be true, and I'm gonna nullify the soul of the other cat. Right, so this transfers the soul from the old cat to the new cat. Yeah, and lastly, I'm going to add a meow function here because the cat can make a sound. And that's all we're going to have for the cat. So we assert that the cat must have a soul in order to meow, right? And otherwise, after that, we just make the sound. So if this has soul variable is a bit confusing and all that, don't worry about it. This is actually just here to kind of help us understand ownership model a bit better. Um, and if you don't understand this part of it, just treat it as we're only going to have a single cat. And it's just this, all this code is just custom logging for when the cat is born and when the cat dies, right? And helping us keep track of the lifetime of the cat. Because later we're going to move the cat around into different ownerships, into different objects and scopes. So it'll be nice to keep track of where the cat is being disrupted. Okay, so with that out of the way, we have a cat that's living and breathing, and now we need a person to play with the cat. So that brings us to Alice, who Alice loves cats. She absolutely loves cats so much that she wants to have a cat as a pet, right? So she might not have a pet, right? She might not have a cat, but if she has the option to, she definitely wants to adopt one. So that to encode the semantics that Alice kind of wants a pet, we have a pet field over here, which is a stood option of cat, so she can either own one cat or zero cats. Yeah. And we're also going to it's also going to be nice if we lock the if we lock the construction and destruction of Alice. And I'm aware that I'm missing some like Simon operators over here, move Simon, copy assignment, but it's not going to be important for this video, so please don't nitpick on it. And we're going to have a back to Alice, we're going to have a custom constructor and destructor that just locks when Alice is constructed or destructed. And so, yeah, that brings us to the main function over here. So we have a cat right now here, C, that's create some beginning of the world, and we create a cat C. We see the cat is born into the world. And then at the end of the world, because the cat is owned by this scope, the cat dies after the scope ends. And we see that Alice is living within this inner scope, right? So Alice doesn't live the whole lifetime of the world, right? Alice actually has a shorter lifetime, and we see that Alice is born and Alice dies here, before the end of the world and before the cat dies. So if this idea of ownership and lifetime is a bit confusing, I recommend either picking up Rust, or I have another video over here that kind of explains the ownership model from scratch. Yeah, motivated ownership model. So I invite you to check out that 1 hour talk. Um, so I'm going to assume that's kind of a prerequisite. So yeah, so with now we have Alice and we have a cat. Let's let Alice interact with the cat. So how we may initially want to do so is if we have a method here called play and takes in a cat C, and we say we just log that Alice is playing with the cat, and we're gonna try this. But what's gonna happen is we see when we try to call Alice.play C, try to pass the cat to Alice play method, we're actually gonna see a use of deleted function compilation error, saying that we're trying to invoke the copy constructor of the cat, but remember we deleted a copy constructor over here, so we got compilation error. And that's because when we have a cat C like that, just by itself, just cat, this is actually trying to take a this is essentially trying to say that play is taking a copy of the cat, and we are not allowed to, and because we deleted the copy constructor, we're not allowed to clone the cat. And so this actually doesn't work. And so what we actually need to do is we can modify it such that we put ampersand over here, and that indicates that Alice is taking a reference to a cat, right? So under the hood, you compile this down, you see that all that's being passed around is pointers, and Alice is taking a pointer to the cat essentially, but references kind of wrap the pointer semantics with a bunch of benefits that I outlined in other talk. But this is actually saying that Alice can borrow the cat, right? If this is unfamiliar terminology, I recommend you check out the other video or other videos online to learn about ownership model. But essentially, a quick rundown would be that when Alice takes a L value reference to a cat here, she can borrow the cat for the time being, and after the scope ends over here, she must return the ownership back to to the caller of play. And so over here we can log that Alice is playing with the borrowed cat. And what we see here, we see that indeed Alice is born, then Alice plays with the borrowed cat, and then after that Alice dies, and the cat dies only after the end of the world. Right? So the cat's ownership still remained within the main method. And yeah, so that's cool and all. But Alice in this case can only borrow the cat to play with. She wants to Let's allow Alice to take ownership of a cat and adopt it as a pet, right? So suppose we have a to do so we have a cat with double ampersand over here, which indicates that C is a R value reference to a cat, and this indicates that um, this method can take ownership of C. And so, there's a small nuance over here, which is that just because Alice can take ownership of the cat doesn't mean she needs to take ownership of the cat. So, what what she can do is she can play with the adoptable cat right over here, which she can theoretically adopt and take ownership of, but she don't need not to, right? So if I show this example, right? So in order to invoke this other overloaded play method, I need to pass in a R value instead of a L value. So to do so, one of the ways of doing so would be instead of alice.play C, I would call alice.play stood move of C. And essentially, this converts the L value C into an R value. And this expression is an R value, which means that it binds to the R value reference method over here. And now what do we see? We see that Alice plays with the adoptable cat, right, instead of the borrowed cat. Okay, that's great. So, yeah, so now Alice plays with the adoptable cat. Um, but there's something, we now Alice doesn't just want to play with the adoptable cat, right? She actually wants to adopt the cat if she can. So that motivates us to replace that with the following two lines of code. So now Alice, in this case, we say that Alice adopts a cat, and how does she actually adopt the cat? How does she actually take ownership of the cat? In this case, we'll call stood move on C, right? So the fact that Alice can take ownership can take ownership of this CEO here, means that she is allowed to call std move on it to pass the ownership to other methods. And when she calls std move on C, that converts a C into a R value, and then the emplace would then take ownership of it and pass it and kind of take ownership, and um now optional will own the cat. And so actually Alice, to nitpick, Alice isn't exactly owning the cat in this case. Alice actually owns the optional, which then owns the cat. But for the semantics of our example here, we can just say that Alice owns the cat, right? So this is the actual adoption procedure where Alice now owns the cat. And how we can see this very clearly is that now we see that Alice adopts the cat. That's just a print statement. But more importantly, when Alice dies, right, the cat dies as well. The cat doesn't wait until the end of the world until it dies. And so if I just comment this part out over here, you can see that the cat dies moves to the end of the world. And so this very line moves the ownership from the main scope into Alice. And now Alice owns the cat. Yeah. So once again, just to reiterate, there's a subtle point over here which is always emphasized in all the lectures you see on value categories, which is that std move doesn't actually move anything. It only marks it as available for moving, and only marks it as, like in this example, it only marks it as available for adoption. But it actually doesn't force Alice to adopt the cat. So yeah, so that's cool. And one thing to note is that it's actually undefined behavior to access the cat after we have called std move on it, meaning that if I call c.meow after it, if I call c.meow, we see that the assertion over here has failed, right? So to illustrate this, if I just lend Alice the cat to play with, in this case, I'm just lending, the main scope is lending the cat to Alice for her to play. We see that meow does successfully print after that. But if we call std move on C and then we call meow, right? We cannot do that anymore because after we mark it as std move, right? The main function doesn't know what Alice did with the cat, right? Because the main function said, hey, Alice, you can adopt the cat. The main function could have lost ownership of the cat, and it'll be undefined behavior to continue using the cat as if the main function owned it. So yeah, so that's great and all, right? And now we see that Alice can adopt the cat, and now all the ownership stuff is settled. Okay, that's great and all, but I would like to pause a little here and kind of emphasize a bit about why this is important, right? So you may already know this if you are familiar with most semantics and ownership model, but the reason why we like to have different scenario, different this overloaded method over here, where one indicates that this Alice can borrow the cat, and one where you can take ownership of it. It actually extends to other software engineering scenarios where this cat kind of represents a resource, right? Represents a resource that may be expensive, may be a huge resource, and in some cases, Alice could represent a service that needs a resource. And if she's given the ability to borrow the resource for a while, she can use the resource. But if she wants her own copy of the resource, she needs to clone it, right? Um, and in the example of cat, we are unable to clone it. But for example, if we have something like a huge vector, right? So cat is like a vector of 1 million entries. And if we can clone 1 million entries, right? We can clone the vector, but be very expensive. So imagine a service that borrows a resource, borrows a huge vector. If they want their own copy of it, they need to clone it, and that'll be very expensive. Um, and what the move semantics allow you to encode is the idea that if the caller calls play, right, or some method of this service, and the caller actually does not need the huge vector anymore, right? The caller is saying, hey, this huge vector, I actually do not need it anymore. You can do whatever you want with it. Then we realize that the service does not actually need to clone the huge vector. Right? The service can just take ownership and kind of like use that huge vector as if it's its own. And so that allows for certain optimization. So it's completely reasonable to expect that a service, in this case represented by Alice, could want to have two different behavior based on whether the caller um, wants to allow this service to take ownership of some huge resource that's expensive to copy. So basically, I'm just trying to say that this toy example in this case is just silly and funny, where we have adoption of an animal, but in a real scenario, this is code that you really do want to write to encode the idea that as a performance as a possible performance optimization, right? Where if you can take ownership of something, you do not need to make the massive copy. You can just take the ownership, and if you have seen the diagrams, it's just a changing of a single pointer instead of copying the entire vector. And yeah, so back to the example. Um, just another side, the ownership model is not just for performance optimizations, but the ownership model is an alternative to garbage collection. Yeah, so ownership model kind of brings all these benefits with it, and this is just a toy example um, for the ownership model. So this is actually really applicable in the real world scenario, and it's not just a toy. Okay, so back to the example. We see that everyone's happy right now, or rather Alice is happy because she can adopt a cat if she's allowed to, and she can play with the cat if she can only borrow it, right? So Alice's behavior is segregated as such, right? Alice's behavior is different if she's given different capabilities, right? If she can borrow it, she, if she can only borrow it, she want to do a set of actions. If she can take ownership, she wants to do a different set of actions, right? So her behavior on this cat differs whether we pass in a L value or a R value cat. But that brings us to Bob, right? Suppose Bob finds cats cute, but he doesn't really want to own his own cat because maybe he's allergic to cats and he doesn't really want to own his own, right? He just wants to go to a cat cafe and kind of play. He's that kind of person that doesn't want a full commitment to owning a pet, but he still wants to play with it. So yeah, so that motivates us to have Bob have his own play with cat function as well as his own that motivates us for Bob to have his own um play function, right? Play method. And in this case, we may say something like Bob is playing with the cat, and this may be just some generic code, and let's just edit it such that Bob can play. So we create a Bob, and now we say that we are lending the cat to Bob to play, and we also want to comment out this one. If not, we get undefined behavior. Yeah, so now Bob is created and Bob gets to play with the cat. The main scope is lending the cat to Bob once again. And we see that, what do we see? We see that Alice is born, Bob plays with the cat, and then Alice dies, and then the cat dies at the end of the world. So yeah, this is just basically this is what we see earlier. Just as Bob instead of Alice. Suppose Bob is um we also want the suppose Bob is a nice person, and if he is if he's borrowing the cat, he wants to let because he's friends with Alice, he wants to let Alice play with the cat as well. So that motivates us to have say something like that, where if Bob gets the chance to play with the cat, gets to borrow the cat, he after he's done playing, right, he wants to pass Alice the cat for her to play with, right? So yeah, so this he passes the cat to Alice, right? And remember that all this time he's still borrowing the cat only, right? Cannot bring it home, right? He cannot bring the cat home. He cannot take ownership of the cat. He cannot adopt the cat, but he can play with the cat. He's just borrowing the cat for the time being. Later, the cat needs to return to the main scope. So because he's trying to invoke Alice play over here, we need him to have a reference to Alice, and that's why we're gonna change the constructor to be something like that. And now we need to edit the constructor such that I pass in Alice, and now Bob has a L value reference to Alice. So what do we see over here? Um, we see that Bob plays with the cat, and then now Alice gets to play with the borrowed cat, and then yeah, and then the cat still dies after the end of the world because the cat's ownership still remains with the end of the world. Still remains with the main scope. So the cat is only destructed after the main scope finishes. Suppose we now extend this to a scenario where Bob can take ownership of the cat, and in this scenario, because Bob doesn't actually want to adopt the cat, he's just gonna play with the cat the same way as he would if he's borrowing the cat, right? He doesn't really care. um, about adopting the cat. So he plays the cat in the exact same way. And yeah, so if we now call bob.play stood move on C, this converts once again the cat to a R value, and it binds to Bob's play R value reference method over here. And Bob is allowed to take ownership of the cat, but remember Bob doesn't want to. So what do we see over here? We see that Bob plays with the cat. This in this scenario, Bob plays with the cat, and then that's all, right? And sadly, right, in this scenario, because Bob is offered the ownership of the cat, but he doesn't actually care much about taking ownership of the cat, right? We see that this cat becomes a stray cat, right? Because right after this, um, this creates a stray cat, right? Because the main method, the main function, the main scope is calling stood move on C, which means that the main scope cannot touch it after that because the main scope has offered the cat up for adoption. The main scope doesn't know if Bob actually took ownership of the cat, right? Because the main the main method just say stood move, you are allowed to if you want to. I don't know whether Bob actually does take ownership of the cat. So if we call stood move on C, using C after stood move would result in undefined behavior. Um, okay, this is not yeah. So calling stood calling C dot meow on after stood move on C is actually undefined behavior, and that's sad, right? Because now Alice cannot take ownership of the cat, right? We cannot call like Alice dot play stood move on C. We cannot do that anymore because um it's undefined behavior. We can only stood move on it, and after that we cannot do anything else. And that's sad because Alice Bob didn't take ownership of it. Um, and now the cat dies after the end of the world, and the cat has no owner, right? Yeah. So the key idea over here is that we want we want Bob to say that if he's offered ownership of the cat, he can actually pass on that ownership. He can actually forward that ownership to Alice, right? And he knows because Bob is Alice's good friend. Bob knows that Alice loves cats, and if Bob is offered the opportunity to adopt a cat, he actually wants to say, "Hey, I love cats. Sorry, I love cats, but not as much as you, Alice. And I actually want to I actually want to forward that offer to take the ownership to Alice." And how that will play out is that we will call stood move on C if in Bob's R value reference to cat play method overload. And so this is great and all because now we see that if we call stood move on C and pass it to Bob's play method, it'll come in here. Bob plays with the cat exactly as he would if he played with the cat while borrowing it. But after that, he actually calls stood move on C to forward that ownership, right? He's done playing with the cat, he doesn't want to adopt it, so he lets Alice adopt it instead. And so now we see that the ownership of the cat has rightfully passed on to Alice, right? Has rightfully been transferred to Alice because Alice play method um, can adopt the cat. So this is great and all, and basically everyone's happy in this case, right? We call bob.play. So in both scenarios where we call bob.play on C, where Bob only can borrow the cat, Bob will play with the cat, Alice will play with the borrowed cat, and the ownership will be transferred back to the main method after that. But in the other scenario where we call stood move on C, Bob plays with the cat, Alice adopts the cat, and then now Alice has ownership of the cat. So this is great and all, and everyone's happy, except the programmer, right? Because the programmer now has to write kind of a repeated code over here. We see that this plays with cat is Bob doesn't care much about whether he can own the cat, right? Bob just wants to play with the cat. And this code is exactly the same in both scenarios, right? In contrast with Alice, right? Alice's code is different. If Alice can take ownership, she'll do a different set of actions, right? Whereas Bob's set of actions is exact same thing. So if we code it something like that, um, that would kind of violate the do not repeat yourself principle. And if we want to edit more parts of the code like that, if we want to, I mean, repeated code is always bad because if you change something like that, then in order to maintain the same semantics, sorry, in order to maintain the same semantics, you need to do this. You need to copy the code elsewhere, and that's a bad software engineering practice in general. So what's the solution to this, right? The solution to this is where universal references and forwarding comes in. So we're going to have instead of writing two methods with two different type signatures, I'm going to have a template type named T like this, and this T is, the cat is going to be this T. And now C, what is C? C is seems like a R value reference, but this T over here is a templated type parameter, and in C++, we actually call this that C is a universal or forwarding reference, right? There's a bit of debate on what kind of terminology is best, but um, C is actually uh, the type of C, the reference type of C actually depends on what you pass it, right? So in this case, we have the same code, right? Bob plays the cat 1, cat 2, cat 3, in the exact same way as he would in both scenarios, right? Now we see that instead of writing the code twice, we only write it once over here. But now we kind of need this like split in logic, right? We need this conditional to say that if the type C is the L value reference, right? So if you pass in, so this is where type deduction comes in, right? If you pass in, if you pass in a C like that, essentially we are calling the type deduction rules would say that this is a L value reference like that. And if you pass in stood move, right, essentially the deduction will be something like that, where it's a R value reference. Yeah, it's a R value reference. So now depending on what we pass in, right, whether stood move or C in the main method, depending on what we pass in the main method, um, that would result in different inferred type parameter T over here, and hence different inferred type reference type for C over here. And we have this if else statement that segregates the two, right? So if this is just some meta programming to detect what type C is, right? So if C is an L value reference, so if C is an L value reference, right, that means that Bob is borrowing the cat. And if Bob is borrowing the cat, he cannot, right? He cannot mark the cat as stood move, right? He cannot stood move it because he doesn't own the cat. You can only stood move something that you own, right? So he cannot, he can only lend the cat to Alice after that, right? But if in the other case where C is an R value reference, and Bob is offered ownership, if Bob is offered ownership, then he can, if Bob is offered ownership, then he wants to forward that ownership, the offer, he wants to forward that offer to Alice. Right? So he's forwarding that offer. He's forwarding that offer of the ownership to Alice because Alice is the one that wants to adopt the cat. So we see that by using this thing called universal reference, doing this template type parameter thing with a T ref ref, by using the universal reference, we can write the same code that will execute in both scenarios, and then we can write some code that would split the logic according to the reference type of C, right? And this whole chunk of code over here is essentially stood forward, right? So stood forward is a nice shortcut for essentially this logic, right? Where if we look at the reference, we see that when T is a forwarding reference, blah blah blah. Sorry for the flashbang of the light mode, but we see that yeah, this overload forwards the argument to another function, right? How Bob is forwarding the cat to Alice, right? Bob's play method is forwarding the cat to Alice's play, and it says that it forwards it to the another function with the value category it had when passed to the calling function. So what we pass to wrapper, right? The value category that we pass to wrapper, right, is being forwarded the to another method, to another function, right? And we see that yeah, essentially this example shows it forwards as R value, L value or R value depending on the type T, right? And the reason why we cannot always just pass in arg is because if we were to just pass in arg, right? If we were just to pass in, we just to call Alice dot play C like that, right? Then that misses out a crucial part where that misses out the crucial that misses out the scenario where Bob is given the offer of the ownership, but he only lends the cat to Alice, right? And doesn't adopt it. So if if we just naively call Alice dot play C, then what will happen if we call what can happen if we do this scenario is that Bob would play with the cat and he only lends Alice the cat over here, right? And we see that the cat's ownership is not the cat doesn't get an owner, right? Alice wants to adopt the cat, but by doing this, we are missing out the opportunity, right? And essentially, you if you just pass in C here, you lose the you do not forward the ownership correctly. So that's why we need that's why we need stood forward, right? So stood forward once again is essentially segregation where if the C is a L value reference, then it would lend the it would lend a cat to Alice, right? Preserving the semantics that Bob is only borrowing the cat, right? And not calling stood move on it to transfer the ownership to Alice. And if Bob is offered the ownership, then he wants to just forward it simply, right? He does the same set of actions, but he forwards it. So yeah, so this essentially captures the essence of universal references as well as the stood forward. They're often hand in hand, right? So often you see this as well. And essentially, um, yet one common scenario is when you see arguments being passed to a lambda, right? Often you'll see things like that. And essentially you want to use a universal reference when Bob, in this case, doesn't really want to segregate his behavior, right? He wants to do the um at the last level, you want to forward it down when you pass an argument to, let's say, Charlie, which passes to Bob. You just want to forward that value category all the way down to the base scenario where Alice is able to make a decision based on that, right? Alice is able to make a different decision based on the value category, but the intermediate steps along the way, right? The intermediate functions, they do not want to make a decision, they do not want to segregate it, but they still want to write the same bunch of code, right? So, yeah, so you can imagine the whole chain of functions that don't really care about the value category. They don't really care about the value category of the parameters they're passed. And because they're acting the exact same way, whether they are offered ownership or whether they're just borrowing it, and they do not want to kind of like prevent the subsequent methods that they call, prevent the subsequent functions that they call from, they do not want to make the decision for the subsequent functions, right? They want to forward that option, that they want to forward that option, um, yeah, they want to forward that ability down to the deepest methods, and only when you hit some kind of base case, then is the behavior different according to the value category. So that's the purpose of stood forward. I hope this video has properly motivated it. If I made any erratas, please leave a comment. And if you liked it as well, please leave a like and leave a comment. And yeah, that's about it. Leave comments for other video ideas you want me to talk about. And if not, I will see you next time.